Okay, so continuing on with pendulums, now we're going to look at how to use conservation of energy to calculate the speed or the height of a pendulum. So read example 2 and pause the video and then come back. Okay, so I've added this diagram in to example 2. So let's just see here. So this would be our ceiling. And then down here somewhere is the floor. And it tells us that when the pendulum is at its highest point, the pendulum is 25 centimeters above the floor. So that could be either talking about position 1 or position 5. It doesn't matter which one. We're just going to say it's position 1. Okay, so this is 25 centimeters. And then it says, what is the height of the pendulum when its speed is 1.4 meters per second? So we don't know whether the speed is 1.4 at position 2 or position 3 or somewhere in between the two positions. It actually doesn't really matter. We're just going to pick one of them and use that. So let's use position 2. So we're just going to say that at position 2, we know that the speed is 1.4 meters per second, and we want to find the height there. So remember that when you're doing energy calculations, you want to pick an initial snapshot and a final snapshot. So for me, I'm going to say my initial snapshot is at position 1, and my final snapshot is at position 2. And I'm just going to make my variables list over here. So for the initial snapshot, the speed there is 0. Okay, and that's because we know that when a pendulum is at its highest point, the speed is going to be 0. And then the height initially is going to be 25 centimeters. We don't really want to work in centimeters though. Let's convert that to meters. And now let's write down what we know about the final snapshot. So we know that the speed at the final snapshot is 1.4 meters per second, and we want to find the height at that point in time. So we're going to set up a conservation of energy equation, just like we did earlier in the unit. So total initial energy equals total initial energy plus work equals total final energy. Total initial energy is made up of EKI plus EPI, and then we have this plus work. And then total final energy is made up of EKF plus EPF. Now we're going to go in and we're going to cross out things that are 0. So since VI is 0, EKI is 0. And also, we're going to assume that this is a closed system here. So the question does not mention anything about friction acting on the pendulum. It also doesn't mention other forces acting on the pendulum. So because it's a closed system, we can say that the work is 0. Okay, so now let's rewrite our equation. So EPI, that's mghi, and then we have our equal sign. EKF, that's 1/2 mvf squared, and then EPF is mghf. Now, if we see mass in every term, we can cross mass out. So I do see mass in every term here. So I can cross that out, and now I'm just going to rewrite what the equation looks like without mass in it. So GHI equals 1/2 VF squared plus GHF. All right, now let's put numbers in there. So let's go ahead and do that. So G is 9.81. HI is 0.25 meters. Then we have 1/2 times VF, so VF is 1.4 meters per second. Don't forget to square that. And then we're adding that to GHF. And since I don't know what HF is, I'm just leaving GHF as variables right now. Putting this in my calculator, so 9.81 times 0.25, that's 2.4525. And the units for that would be meters squared over seconds squared. And then 1/2 times 1.4 squared, that's 0.98 meters squared per second squared, plus GHF. Okay, now our goal is to eventually solve for HF. So we want to get HF by itself. So let's subtract 0.98 from both sides of the equation. So we're going to have 2.4525 meters squared per second squared minus 0.98 meters squared per second squared. And that's going to be equal to GHF. Okay, so when I actually do the subtraction there, I get 1.4725 meters squared per second squared, and that's equal to GHF. So now we can see that if we want to isolate for HF, we need to divide both sides by G. So 1.4725 meters squared per second squared divided by 9.81 meters per second squared, that's equal to HF. And when you do that, you're going to get 0.1501 meters, or for a final answer to 3 significant digits, 15 centimeters. Okay, again, read example 3 and then come back. Okay, so here we have a 1.5 meter long pendulum. So that's saying that's the length of the string. And it's lifted to 30 degrees above its equilibrium point. So the equilibrium point is right here. It's where the pendulum hangs straight down. And so what it's saying is that this angle right here is 30 degrees. And we want to know the maximum speed of the pendulum. So in the previous video, we learned that pendulums go fastest when they're passing through the equilibrium point. And so really we want to know the speed right here at equilibrium. Okay, so let's see what else we know. So if we call this the initial snapshot over here, we know that over there, the initial speed is 0. And you know what, let's call this one, when it's passing through equilibrium, let's call that our final snapshot. So we'll write down VF is question mark. Okay, but now we need some heights to work with, and we need to be careful because 1.5 meters is not the height. It's just the length of the pendulum string. And there's one more thing we can add to the diagram here. If we measure from the top of the pendulum to the bottom of the pendulum, that's going to be 1.5 meters. So we have 1.5 meters showing up in 2 places, right? And the length of the pendulum doesn't change just because the pendulum moved off to the side. Now, remember that when you're doing conservation of energy questions, you need to choose what you're going to call your 0 height. And so here, I'm going to make this line that I'm tracing over in green. That's going to be my 0 height. And the reason I'm putting it there is because now I can actually say that HF equals 0, and it makes the math a little bit easier. Okay, but now I need to be able to figure out what HI is. And HI is going to be whatever this distance that I just wrote down in red is. And so to figure out what HI is, we need to actually do some trigonometry. We need to turn this pendulum into a triangle. So the triangle that you're going to make is going to look like this. I'm going to trace over it in green. Okay, so I'm making a right angle triangle. And what I'm going to do is I'm going to find out what this side of the triangle is using trigonometry. So just focusing on that green triangle that I traced over for a second, we can see that this 30-degree side is adjacent, or sorry, this side that I just wrote adjacent next to is adjacent to the 30-degree angle. So we can write down cos of 30 is adjacent over hypotenuse. So that's adjacent over 1.5 meters. And so to find the adjacent side, we're going to have to do 1.5 meters times cos 30. And when you do that, you get 1.29 meters. So going back over here, this is 1.29 meters. Okay, now think about this. So HI here would be this missing distance. I didn't draw my diagram perfectly, but if all of this is 1.5 and then all of this is 1.29, hopefully we can agree that HI would just be 1.5 minus 1.29. I'm just going to put things back where they were. Okay, so HI is 1.5 meters minus 1.29 meters. And remember not to round any numbers yet, so we're going to use not just 1.29, but the full value that shows up on our calculator. And that's going to give us 0.20, and it keeps going, meters. Okay, so now that we have figured out what HI is, we're actually good to go. We can set up our equation. So it's going to be very similar to the last example now. We're going to jump right to this point. So we're going to have EKI plus EPI plus W equals EKF plus EPF. And again, let's cross out things that are 0. So since VI is 0, EKI is 0. Since HF is 0, EPF is 0. And again, since it's a pendulum and we know energy is conserved and the question doesn't mention friction, work is also 0. So we have just EPI equals EKF. So EPI, that's the same thing as MGHI. And EKF, that's the same thing as 1/2 mv squared mvf squared, I should say. Okay, now I check if there's mass in every term. Mass is in both terms. So that means I can cancel out the mass, and I have GHI equals 1/2 VF squared. Okay, and now I'm going to continue over here. So I'm going to rearrange for VF. So I'm going to multiply both sides by 2. That gets rid of the 1/2 in front of VF squared. And then I'm going to square root, because I don't want VF squared, I just want VF. You might be wondering why I rearranged here first before plugging in numbers, whereas in the last example, I plugged in numbers first. It just has to do with how complicated it is. So this formula here that I'm circling isn't a very complicated formula, so it's easy enough to rearrange. But when I was doing this example, the formula that I had was a little bit more complicated, and so it was easier to just put numbers in first rather than trying to rearrange. Okay, so plugging in values here. So we're going to have 2 times 9.81 times HI, which we found, and it's 0.2. And we have to remember to square root all of that. And whatever that is going to be equal to VF. When I do that, I get that VF is equal to 1.985 meters per second. And here we only want 2 significant digits because the angle is only to 2 significant digits. So after rounding, we're going to get 2.0 meters per second.